Okay. Now, for today's class, we're going to try something a little different, and it's part of, my own homework, because I've been participating in a workshop on active learning, and so with each module, we take some technique that's been discussed and try it on class. And for most part, I've been trying them out on my other class, 285 DE, and most things have not gone well because undergrads can be pretty difficult. So I'm hoping that trying something out on a small class of graduate students might work better than on a large class of undergrads. But we'll see. But this is why I suggested you take a look at certain notes, because we'll be making a transition from what I covered in both sections to now. And it may be kind of unusual for a math class, but I want to try to structure today as we segue into the next topic to be a bit more discussion oriented. And like I said, it's kind of unusual for a math class, but we'll just see how this goes. And so, and the nice thing is, there's only 6 of you, and you all know each other, and so it should be a nice, more comfortable setting than in a class of undergrads where most of them are really like, I don't want to be here. So, yeah. So it's pretty experimental, and then after this is over, I get to write up what happens, and see if I score 9 out of 9. So, okay. So the and also actually what I considered doing for a discussion-like format is have a different arrangement, or maybe like it's not like me lecturing at the board, but like having the space arranged more of a group discussion. Except we do have at least 2 people who watch this, so unfortunately we still need the board. That doesn't mean I have to be the person writing. So again, we're seeing how things go. If someone wants to come up to the board and do something, as opposed to me like serving as the scribe, that would be fine too. So this is very free form. And really the whole point of one of the whole points of active learning is, or major aspects of it really is, to get away and not be just straight lecture, which I've pretty much been in this class. It's usually at an upper level. Okay, so first I want to give some context to start things off. So the only kind of matrix we're going to be dealing with for today is symmetric, positive definite matrices. And as usual, we are concerned with problem solving AX equals B. And I'm also going to make some assumptions. Besides the fact that A and B is symmetric, positive, definite, and of course n by n, we'll assume that A is a large matrix. Also, we're going to assume that it's sparse. So most of the entries are 0. Okay, so to kick this off, and this I considered calling on people. At some point I might do that, but I'll try not doing that and again see how it goes. But if we have long periods of silence, I'm calling on people, so you've been warned. Tell me some approaches we could take that things we've seen so far that could be used to solve this kind of system under these assumptions. Okay, so let's Gauss-Seidel. Okay. Okay, and just for fun, I'm going to ask, what in particular led you to pick a Gauss-Seidel? Out of curiosity.
Because I read before class.
Yeah.
If you want the truth.
Yeah.
If you want me to make up a math answer.
Okay. Well, let's throw it open to everybody. Like, what would be our reason to pick Gauss-Seidel?
Because it's sparse.
Okay. All right. So throw in a Y column here. All right. Yeah, because what kind of method is Gauss-Seidel? What was it like? How do we classify that?
Iterative.
Yeah, it's an iterative method, and yeah, iterative methods are good for sparse systems in general. Okay.
I was going to say, we know that since it's symmetric, positive, definite, we know it'll converge for Gauss-Seidel.
Yes, and that's actually what I was hoping Stephanie would say. But okay.
Totally what I was going to say. I just didn't give her a chance.
Oh, okay. Yes, teacher in action. Okay.
You know.
So yeah, it's known to converge for those kinds of systems. Okay. What's another method?
SOR.
Yeah, SOR, also an iterative method. Now, of course, it's the same reasons that apply to Gauss-Seidel would apply to SOR, because Gauss-Seidel is a special case of SOR. But now, what about SOR? What's a good reason to choose SOR over Gauss-Seidel? We'll make the methods compete.
Doesn't it converge much more quickly?
We have to determine omega.
Yeah.
Right.
Yeah.
Find a good relaxation parameter.
So it should say it can converge faster. Now, the example that I did in section 5.2, where I tried Jacobi, Gauss-Seidel, and SOR, I cheated and found the best omega that had made the convergence as rapid as possible. So it can converge much faster. Okay. What else we got?
Jacobi.
Jacobi. Okay, I can think of one good reason in particular to choose Jacobi over the other two that we've seen so far.
You can do all the rows simultaneously. Or
Yeah, it's parallelizable. Okay. Okay, so we have some virtues here. Now, okay, I think a couple of you were hitting on this earlier, but I want to put it out there clearly for everyone to hear, because it's been said that SOR can converge faster. But how is this plus also a drawback?
What, SOR?
Yeah.
you have to spend time finding the relaxation parameter.
Yeah, because we don't know how to find it. Like for certain classes of matrices, it's known. But even then, I gave a formula for it in the tri-diagonal case, and it still relies on a spectral radius of something else. So yeah. But so if it's not in that category, it's like, okay, what do you do? Okay, so what else? Is there anything else that's specifically built for symmetric positive definite? That is SOR.
Okay. That's right.
Yeah. Okay. So these two are iterative methods also. Okay. Now, let's see. Okay. I'm going to drop my qualifying phrase here specifically for symmetric positive definite. Any other method at all for this problem? What did you say? That's really what I was looking for.
Okay.
Yeah. So Cholesky which is a direct method, and Stephanie, you were saying,
So Gaussian
yeah, we'll write that down too.
Cholesky's only for positive, symmetric positive?
Yes, Cholesky will fail if it's not, because you'll either take square root of a negative number or you'll divide by 0. Okay, now, all right, so we have some direct methods and we have some iterative methods. But since we have two direct methods, why Gauss elimination now work for any system that has a unique solution? So, can anyone give me a reason to choose Cholesky over Gauss elimination?
The flops, I can't think of
You
like the,
recompute.
Faster.
yeah.
It is.
That you already have.
What word did you use though, like it's not as costly or.
Yeah, well, the number of flops is less.
Right,
Yeah. Cholesky is half as many flops, floating point operations, as Gauss elimination because of the symmetry. Because instead of computing an L and a U, you
Transpose, so you're just doing one of them.
right, yeah, so that's exactly what cuts it in half. Okay, now, keeping in mind that this is a large sparse system, though, so clearly among direct methods, well, actually, there's one more direct method. I didn't really spend much time on it, but it was out there. I could say one more factorization. So Gauss elimination is like PA equals LU. Cholesky is A equals GG transpose. There's one more factorization that I briefly visited that could be used for symmetric positive definite systems. What? Well, we haven't covered more than that one. That could be, but that's not the one I'm looking for.
That's the LDN.
Yeah, well, LDMT, but for the symmetric, it's LDLT. So, okay. Now, LDLT has the same benefit in terms of symmetry as Cholesky. It's because you have, D is a diagonal matrix, and you have the L and its own transpose on either side of it. Can anyone think of a reason to use LDLT over Cholesky?
So I have to do is fill in because it's not sparse.
I don't know, I can't remember what G,
That's-
what G looks like.
G is lower triangular. L is unit lower triangular.
And then the diagonal and then.
Is it because of uniqueness?
No, uniqueness is not an issue for everyone. But, if we compare LDLT and versus G transpose,
It's the diagonal, but I don't know how, like,
yeah, it relates to the diagonal.
yeah.
So, what would be a way that could be
We already have, we just get the diagonal like free sort of, because it's like.
and there's actually another name for LDLT. It's something Cholesky. It's because it's so closely related, but okay. Or you can also see if I'm trying to express this, like, is there a different way you can express G in terms of L and D? Because this is a similar structure going here, lower triangular, lower triangular.
Yeah. D as L and, or G as L and D.
Right.
Square root.
Okay.
Square root, right?
Yeah, so I could say G is equal to, like what would be a formula for G in terms of L and D? sort of square root is needed.
I know what it is, because I'll look at it, so I don't want to.
Oh, okay.
Yeah, I just found it in the notes.
Okay.
LD to the 1/2.
Yeah, LD to 1/2. Yeah, so that's why LDLT is called the square root free Cholesky, because it's very similar to Cholesky, but if you look at the algorithm for Cholesky, it requires square roots. We saw that. Working through examples. Square root is, it's not one of the 4 standard operations. I mean, computers are hardwired to do add, subtract, multiply, and divide. They do other operations like square root, log, exponential, sine, cosine, using approximations. It could be based on Taylor series, or it could be Newton's method, something like that. So, and we count all flops as being equal, but they're not really. Well, first of all, among the 4 basic flops, division is the most expensive, slightly more so than multiplication, and both of those are much more expensive than addition and subtraction. And then anything like a square root is more so. And I'm thinking, I can't really say, oh, a square root counts as X number of flops, and we don't really drill down to a level of detail, but it's something to keep in mind when assessing efficiency. So because LDLT doesn't need any square roots, you could argue it's just slightly more efficient than Cholesky. Okay, but what about, since we have some iterative methods and then some direct methods, what do you think is a better choice of type of method? Direct. It would say, we can pick the best iterative method. We can pick the best direct method, but
Depends on what you need, right?
Yeah.
Because if you don't need an exact solution, then you don't need to use.
yeah, that iterative makes sense because you can quit early.
Right.
Do less work. So it certainly makes sense in that case. Now let's suppose, so let's take that situation out. Let's suppose we really do want high accuracy.
Oh, so we're still assuming A is large, is sparse?
Yeah, that we're leaving an assumption in.
Well, I mean, in the notes it says that direct method can cause fill-in, but I guess I just don't know exactly what fill-in means.
Oh, pivoting. It's a consequence of pivoting. Because your matrix has a nice sparse structure, then you do some pivoting, and also
And then
new
it's not-
non-zeros are created, and your sparsity is lost.
Right.
Now,
So we would lose our sparse matrix, basically?
right, yes, but,
See,
yeah.
I don't understand why by creating new zeros, sparses is lost. Why?
Well, because that's what sparse means, to have mostly non-zero entries, but now you have fewer non-zero entries.
Oh, okay.
Yeah. But let's bring in the fact that our matrix is symmetric, positive, definite. Now, what is a way, a way to test for whether a matrix is symmetric, positive, definite? It's actually related to how we could check whether the LU decomposition of a matrix even exists. And now I'm talking about without pivoting. Because every invertible matrix has this decomposition, but not every matrix has an LU. If you're just given a matrix, it's symmetric, because you can easily check that.
Yeah.
And it has positive diagonal entries, you can easily check that. But what's a way to confirm that it's symmetric, positive, definite?
The determinant?
Yeah, the determinant of,
Bigger than zero.
well, the whole matrix, but also whatever matrix, not just the whole matrix, but
Any sub-matrix.
Yeah, the principal submatrices. Yeah. So the thing is, and all of them have to be positive. So if all of them are positive, you can do Gaussian elimination without pivoting. So that would be an argument in favor of a direct method again. So you can say, all right, so let's suppose you want high accuracy, and you can say, well, because it's positive definite, you can say, well, I just won't pivot. So you don't have to worry about fill-in. So that takes a couple arguments in favor of iterative method out of the picture. Also, let's assume that we don't have any initial guess. If you're iterative method, all you can do is to say, well, we'll use initial guess of 0. Now, I'll throw in another assumption. And what if A is banded? Or I'll make it more concrete. Tridiagonal. If we were to go ahead and we have a symmetric positive definite tridiagonal matrix, and we do, for instance, Cholesky, we know G is lower triangular, but in this case, what more can we say about G, like its structure-wise?
You worded it a different way?
Um,
Reword your question.
okay, so if let's assume that A is tridiagonal. Okay, well, when it's tridiagonal, that means so that's a kind of banded matrix. It means there's an upper and a lower bandwidth. So what's the lower and upper bandwidth in that case? Like when it's tridiagonal. There's a low.
I don't know these letters. I mean, I'm reading about it, but I don't
Yeah.
know the letter. I don't know the P
What?
and Q.
Yeah, the same thing I'm looking at.
Yeah. So like if it's tridiagonal, you have main diagonal above and below. So what happens when you have a matrix like that and you go ahead and do, well, it doesn't really matter whether it's LU decomposition, or if you do Gaussian elimination, or if you do Cholesky decomposition, because it's symmetric positive definite. What can you say about your factors? Like, you know G is lower triangular. What?
It's lower triangular.
Well, we know that anyway.
Okay.
But what more can we say in this case? It's better than lower triangular.
Positive?
Well, the diagonal entries are positive, but that's a property of Cholesky. So, but because of this structure where everything else is 0, so what
Isn't it about the cost?
well, yes, that's well, yeah, okay. How expensive is Gaussian elimination normally? For a general matrix?
2/3.
2/3 n cubed. And then we cut that in half for Cholesky, so 1/3 n cubed. But for a tridiagonal matrix, Gaussian elimination is not order n cubed, it's order... Yeah, it's order n. So what happens is, okay, so we could say this matrix here has an upper bandwidth of 1 and a lower bandwidth of 1, because it's tridiagonal. What can we say about the bandwidth of a Cholesky factor in that case?
Why 1?
Well, the main diagonal doesn't count. So, okay. So lower bandwidth is number of diagonals below, upper bandwidth is number of diagonals above, strictly above. Okay, so again, what does this tell us about the structure of a Cholesky factor? Besides the fact it's lower triangular, like, how many... Okay, this is an n by n matrix. How many entries do we actually need to eliminate in Gaussian elimination? Take a stab at it.
Uh,
So how many actual row operations do we need to do if this is n by n? Because you have to eliminate elements below a diagonal.
so just that
So
one.
it's just the one band.
Yeah, so how many elements?
And minus one.
N minus 1. Yeah, so, and the thing is, whenever you eliminate an element, you're doing a row operation, so you have to compute a...
Wait, say that again?
we have to compute, like what, to perform a row operation, we need to compute the, it ends up going in the L. It's a number, but we call this number the, no, the row operation. We are subtracting a blank of a row from another row.
Scale multiple.
Multiple,
Okay.
multiplier.
We're all like.
Okay.
Those two,
What?
You can't
we
get
were
that
all
simple.
overthinking that.
Yeah, okay.
I was thinking it, but I was like, this is. I didn't know how he wanted
Okay.
me to say it. I was like.
For the remainder of this class, stop that. Say something. No matter how gibberishy you might sound like. Some things really are simple. To some of them. So yeah. Okay. And once you compute the multipliers, in your decomposition here, where do they go? Where are they stored? So we're just talking LU now. So where do the multipliers end up? I should have had you guys read further back. Okay. It's stored in L. L has a diagonal of all ones and all the multipliers. So if we're only eliminating these entries, like if I'm eliminating Aij, then my multiplier is an Ij. So if a matrix has a lower bandwidth of 1, then what can we say about the structure of L? It's unilower triangular, but it is also, because if based on what we've just been talking about, of what few entries we eliminate.
It'll be symmetric. Did you already know that it's symmetric? Yeah.
It is in general, but even if it's not,
Okay.
it's enough to say it's this. It's tridiagonal. So we factor this into like an LU, or if it is symmetric positive definite, we factor it into a GG transpose. So if we know that L is unilower triangular, but in terms of where its entries are 0 and non-zero, what can we say? More than that, because of this. So since you only needed to eliminate these n-1 entries that are immediately below the diagonal, and for that you can compute multipliers to do these row operations.
So would it be 0 everywhere except?
Yes.
Diagonal?
Yeah. So
Yeah.
since this matrix, the original matrix has a lower bandwidth of 1, L has a lower bandwidth of 1. And since it has an upper bandwidth of 1, U has an upper bandwidth of 1. So in a symmetric positive definite case, G is, it's lower triangular with only those entries immediately below. We actually say it's lower by diagonal, but I hadn't taught you guys that term yet. Yeah. And bidiagonal matrices come up pretty often. We'll see more of them like toward the end of the semester. So if we want to stick with a direct method, in this case, it's really very little work. So that's a compelling argument in favor of it. But if there's something you know about, like finding a good realization parameter, then maybe SOR is the best choice. So can't really say there's a clear winner in a defense situation, and some people have their preferences. And that's one of the reasons why I wanted to start with this, so that you guys can see, well, it's not so clear cut. A lot of people, in a lot of research, like say, I have the best method. I'm like, yeah, shut up. I mean, and people do develop methods that are the best for certain limited situations. But we're talking about pretty large classes of matrices here. And there are a lot of things to think about. There's, size, structure. What accuracy do you need? That was a good point that you made right there. So much about the context can influence method choice. But now, if we return to the original assumption, symmetric, positive, definite, it will also assume large and sparse. Now, if we decide to actually, whether we're using a direct method where you have to carry out Gaussian elimination or something similar like Cholesky all through the matrix, or you use an iterative method for which you might have to perform many iterations. Of course, there's accumulation of round-off error and so forth. But it'd be a good idea if we can to see if we come up with a whole other way of handling these kinds of systems that doesn't fall into either of these categories. Well, I mean, anything falls into direct versus iterative, and this is going to be iterative, but these we can say more than just iterative methods. There's two classes of iterative methods, and these three are what?
Stationary.
These are stationary. So now let's start taking a peek at non-stationary, and I'm going to stick with this more discussion format for as long as I can, just because, well, it's fun. Okay. I'm not sure how far I'll get, but that's okay. Now, so while there is a homework assignment on iterative methods, those are only on the stationary kind. Okay, so just slip briefly to lecture mode for a little bit. One approach to constructing a non-stationary iterative method that all have this form. Each new iterate is equal to the previous iterate plus some parameter, scaling constant alpha k, times some vector, which is called a search direction. So we have this basic framework, but then we have to ask questions like, how do we choose the search directions? How do we choose the parameters, alpha k at scale? Like, once we've chosen a direction, how far do we go along it? And one way to serve as a guide for constructing an iterative method is, because you need to have some way to measure effectiveness, so you can reformulate your problem, ax equals b, as a minimization problem. Because that way you can readily judge progress. Like if you're trying to minimize some function, and when you hit the minimum, you've solved ax equals b, then you're trying to make the value of this function smaller and smaller. And you feel like the smaller you make it, the more progress you're making. So there's one number that describes progress towards a solution. But how can we do that? And one way is actually dealing with uses calculus. So I'm going to let n equals 1 for a bit here. And we'll have ax equals b, so now all these are numbers. Or what I'll do is I'll say ax minus b is 0. Now, when you are, let's put your calculus hats on. And it's just cal 1. So when you're trying to find a minimum of a function, what quantity should be equal to 0? Derivative. So let's think of this as a derivative, and I'll call this phi prime of x. Okay, so we can think of this as a problem of trying to minimize phi. So in this case, what would phi be?
Does it say phi prime
Yeah.
equals A.
Yes, is ax minus b. So to get phi, we would have to do what?
X
X squared.
integrate.
Yeah. And we integrate 1/2 ax squared minus bx. And so we want that to be a minimum. However, having a derivative equals 0 is not enough. What else do we need? To make sure it's a min and not a max or something else. What?
Concavity.
Constant,
A
A
plus
plus
C.
asking.
Yeah, a, b are constants, but.
Oh no, like adding a constant, cause you're integrated, like plus C.
Oh, right. Nah. No, because if you have a function that it's a minimum, if you shift the function up and down, it's still a minimum. So forget that. Yeah. I'm not being graded for Cal 2, so I don't do a plus C anymore.
Right, without loss of generality. Do you need to check
That's my
concavity?
favorite.
Yes,
Concavity.
concavity. So,
Yeah.
how would I check concavity?
Second derivative.
Second, what is the second derivative?
A.
So, A.
Yeah. So we need a to be positive. And the thing is, that's a parabola, and if a is positive, then a parabola is facing up, and there's a clear minimum. Okay. So now, if we take all this and generalize, so n could be anything again now. Well, since a is a positive number when n equals 1, then the counterpart to that would be what kind of matrix?
Say that one more time.
Yeah.
So instead of having a positive number when n equals 1, if we say a is now an n by n matrix,
Symmetric, positive,
Positive.
Definite. yeah, which has strictly positive eigenvalues. So now we have a being symmetric, positive, definite, and the function is now a function of n variables, so x is an n vector, and I'll just cut to a change here to what it generalizes to, because we need symmetry. It's 1/2 x transpose ax minus b transpose x. So instead of just multiplying, we have matrix vector multiplication, and we now have dot products. Okay, so we want this to be a minimum, and when you have a function of several variables that you want to find a minimum of, so what needs to be 0 this time? Instead of a derivative, instead, if you're talking about several variables, what is it instead? So you want to remember from our multivariable calculus.
Gradient?
Gradient.
Gradient.
Yeah, so the gradient of phi in this case turns out to be, well, it's going to be ax minus b. Okay, so now we want that to be 0. And then if we take the Hessian, that's the counterpart to the second derivative multivariable, that needs to be symmetric, positive, definite. But that would just be a, which is known to be, assumed to be that. So we're good there. Okay, so from a okay. Now, so from a given point, like if we have make an initial guess, like say x naught is 0. So from x0, we want to head out along a certain direction to get to x1 and so forth. So from x naught, we can go ahead and compute our gradient, which in that case would just be minus b, if we assume that our initial guess is 0. But the point is we have a gradient. Now, there's a concept from multivariable calculus, it's called the direction of steepest descent. And does anyone remember what that is?
Sounds familiar.
So minus the gradient of phi at any given x, that is the direction of steepest descent. Starting from x. So along that direction, phi will decrease most rapidly. at least locally. And once you wander far enough away from it, it may not get much decrease at all. So this is not necessarily reliable, but it's some good information to have at least at that point. If you want, since you want phi to decrease. So, okay. So that gives us something to go on, that a search direction. We can say, all right, we want to make phi smaller and smaller until it is a minimum. So we can choose initial guess. We'll say 0 generically. I mean, if you know something about your system, maybe you have an initial guess, but it doesn't matter at this point. So we can start iteration. So we can let pk be equal to rk, which is minus the gradient. Well, the gradient is ax minus b, so minus the gradient will be b minus ax k. What do we call this? When we're solving a equals b, we compute this vector b minus ax. That is called the... There's a reason why I called it rk. What? No.
Residual.
Residual. Yeah. So a synonym of what you thought. Yeah. So okay. So in this approach to solving ax equals b, where a is symmetric positive definite, we are using the residual as the search direction. Okay. All right. So pk has been chosen, but it's still a matter of what is alpha k. So the goal is to make phi as small as possible. So xk plus 1 will be xk plus alpha k pk, such that phi is smallest. So as small as we can make it. So in other words, we now have a more concrete minimization problem. So to find alpha k, I will define a new function. I'll call it g of alpha k, which is phi of xk plus alpha k pk. And we want that to be a minimum. So xk is set in stone. Pk is now set in stone. The only thing that's unknown is alpha k. And we want to minimize that. So, how can we do that? How can we find the minimum? Which we've just been talking about in other cases.
Gradient?
Take a derivative.
Yeah.
Well, now the nice thing about that is we no longer have to take a gradient as we did with phi, because alpha k is a number. It is a function of only one variable now. So by choosing a search direction, you're reducing the dimensionality of your problem from n all the way down to 1. So we need g prime of alpha k. Now if I substitute in what this is, it's going to be kind of messy. Okay, so 1/2 xk plus, well, it's a derivative of all this, so alpha k pk transpose a xk plus alpha k pk minus b transpose xk plus alpha k pk. Okay. All right, derivative of all of that mess. Now, one thing you could do is multiply all this out and then take the derivative. Let's try not doing that to reduce the mess. Instead, we can use product rule. Well, well, actually, we would only need product rule on this part right here, because when you have several factors multiplied together, you just, like, in this case, I have 3 items, the vector transpose A, then the vector again. You would have 3 terms, and each term, one thing is differentiated. We are also differentiating with respect to alpha k. So that's our variable. Everything else is considered a constant. So what would be the like the first term produced by the product rule if we just go ahead and differentiate this and then leave everything else undifferentiated?
Transpose is throwing me off.
Okay.
Do you-
Well, look at this. The derivative of transpose is a transpose of a derivative. So you can, so it's not really going to affect things. You just have to leave it there.
Okay.
So is it PK
Over 2.
Well, I pulled the 1/2 out already. Yeah, you're gonna have PK transpose, and then all this stuff. Okay, and then what term is going to be next?
So now we're looking at
No, now we're doing
Now we're
the,
doing
doing the
the
second one, so it's gonna be the exact same, well, it's gonna be, the first one, it's gonna be the first set of parentheses,
Yeah.
A, and then PK, do you have to leave it in that order?
Yes, you do.
Yes, you do.
Yeah. How come we can skip over differentiating A?
It doesn't involve a.
Yes.
variable.
Yeah, it's constant.
Constant.
Yeah.
Yeah. Okay. So all right, so we have that A times
What is that, alpha, what is that?
alpha k
Alpha.
pk.
Yeah, sure.
Okay. And then we only have to differentiate this. So
And B transpose is a constant?
yep.
PK.
Okay. Now, oh wait. Yeah, because 1/2 is only applying to this stuff. Now, these are dot products, and everything here is real. So dot product is commutative. So in fact, what you can do is I can transpose all of this, and I get exactly that, because A is symmetric. So this could be condensed to PK transpose A so I have 2 of these divided by 2. And then there's still this other thing here. Okay. Now, okay, and we want derivative equals 0. So what should alpha k be equal to?
Well, not,
We can't go over yet.
can't go over. Times
PK
A
transpose inverse.
And A,
Not quite.
Minus
Uh-huh.
PK transpose AX.
Yeah, and actually, to make things a little simpler, I can switch things in dot products. I'm going to do that. PK transpose B. Okay.
Divided by PK transpose A PK.
Yeah, PK transpose APK. All right. Now, can we simplify this a little bit?
Get the PK transpose.
yeah, all the PK transpose.
Yeah, we can factor out a PK transpose, and what's left is B minus AXK. Oh, whoops. Sorry to whoever's watching. Okay. All right. can we simplify anything more?
PK transpose.
Oh,
That's
B
PK.
minus, that's R.
That's PK.
Yeah, it's just RK and PK.
Which
So-
one do you wanna use? Which one are you using?
I'll use P. Okay, over. All right, so now we have a nice compact expression for alpha K. Do we ever need to worry about the denominator being 0?
No,
No,
because it's
it's
positive,
symmetric.
symmetric, definite, it has to be.
Yes, that expression is strictly positive, so that part is fine. Okay, and also the numerator is the norm of pk squared, so that's always going to be positive too. So the whole thing is positive. So now we have a formula for alpha k.
So if we want alpha K to be, I thought we want it to be equal to 0.
Well, that would be the ideal situation because that means we don't have to iterate anymore.
But the only scenario would be if the norm was 0.
Yeah, so there was pk. Yeah, well, pk itself was the zero vector. Yeah, but that would only happen if this was 0, which meant we found our solution. So
So that's not happening.
not exactly, but it's going to get smaller and smaller, presumably. Okay, so this is called the method of steepest descent, because it uses the steepest descent concept to choose the search direction. Okay, and it seems pretty straightforward implementation-wise, and we just have this a couple matrix vector products at each iteration to proceed from one iteration to the next.
Is this analogous to like Newton's method? Because it seems a little bit like Newton's method.
Well,
If we're finding like a direction, sort of like when you divide by the derivative.
yeah, you probably could draw some parallels to that. It's Newton's method is often used to find minimum functions because it's Newton's method is a root finding method, and you're finding the root of a derivative, or in this case, a gradient. Let's see. So if you apply Newton's method to b minus ax, well, then a would be the Jacobian. Well, actually, Newton's step would just solve the system right away. Because the trouble with Newton's is you're actually solving an ax equals b, where ax is Jacobian. Yeah. Okay. Now, but now the question is, now that we have this method, does it really work? And I want to see if I have this here. Maybe I can show you. Okay. Oh, I thought I had. Oh, I do have MATLAB running. But I need to find the right thing. And at least I can show you guys right here, and then for those of you who are watching, I can put the code online. I do have it. Okay, so I'll turn this around so you guys can see. I have a demo of steepest descent solving two different 2x2 systems. But that's because I could use, it sounds kind of asinine, but that way I could use plots to illustrate how the method works and what's good and bad about it. Now, I've chosen two matrices. I've made one matrix that is well-conditioned and one that is ill-conditioned. So, okay. So if you want, you guys can get closer. Okay.
Are we gonna do uploads from the video?
Oh, that's right, we will be.
Oh, perfect.
Okay,
Exciting.
okay. Well, just for fun,
We get front and center.
you know. Okay, yeah, so everybody say hi to Candace and Vivian. Okay, okay, all right. So, okay. All right, so now I get to look at all your goofy faces while you're watching us go. Okay, so what I have here is a plot of phi in the left plot, and there's if I were to rotate this graph, you could tell that there's a minimum to it, right wherever there's darkest blue. And then here I have contour plot of phi. So here's the exact solution where the minimum is, and my initial guess is here at the origin is 0, 0. And what I'm going to do is as I hit a key, I'm going to, you can see an iterate from Steepest descent, and okay. All right, so here from my initial guess of 0, I take my first step right there, and then I take another, and it just keeps going. So what do you notice about how the steps relate to each other? They're perpendicular. That's an interesting property. And so after a few iterations, it converged to the exact solution. Now it's going to. I have here the error. Okay, so it's still not that great, but it's going to keep getting smaller. So now it's 0.007.
Can you zoom in on the graph or not? Is that
I can try that. Let's see. Yeah. And then once the error gets small enough,
it's like no.
it will switch to the second case. Okay, here's an ill-conditioned matrix. So what happens, notice the level curves now are more stretched out. So it's like going from a bowl to a gravy boat. And same situation, exact solution, initial guess of 0. And what will happen is the same, again, it's meant to zoom in automatically to a point. It's still technically a zigzag, but the steps themselves are a whole lot smaller. And this gets really annoying as it crawls and crawls toward a solution. Finding the steepest descent direction at every point, but getting such a small alpha k. And you can see it's getting worse because the curve is getting denser, the steps are getting smaller. And one of these days, it will get there. And look at the error, it's still like 0.1 and decreasing at a snail's pace. It's like, you can do it, you can do it. But it's getting tired. And, well, yeah, it's around 1% error now. Okay. Yeah, so there you have it. So I'll put this code on the site. Yeah, so that's an unfortunate aspect of steepest descent. So let's focus on that one property that could be observed during the iteration, especially the first one, where you can see it better. How these directions, each direction was perpendicular to the previous one. So in other words, what we're saying is that pk plus 1, which is the same as b minus a x k plus 1, is orthogonal to pk, which is b minus, well actually, I'm not going to write pk alpha because I can write xk plus 1 in terms of pk. So that's b minus a xk plus, okay,
Is it alpha?
yeah, alpha k pk. So what we can do is go ahead and take the inner product of pk and pk plus 1. So to prove this, we look at PK transpose PK plus 1. So now write out what PK plus 1 is. So we have PK transpose B minus PK transpose AXK minus PK transpose A alpha K PK. Now, can any simplifying be done here before going any further?
Factor out PK transpose.
Right. Well,
And then
I
B
don't know, I don't
minus
know
A,
us,
B minus AX is PK.
yeah. So we get PK transpose PK from the first two terms, and then alpha K is a constant. We'll pull it out. Okay. And then what can we do?
Okay, wait, hold on.
Okay.
That proof over, where, on the left-hand side of the equal sign, is that right? It's PK transpose and PK plus 1?
Yeah. Taking a dot product.
I was relating it to alpha K, but
Let's go with that. Alpha K. What can we
they
do?
have different subscripts, so I was confused.
Oh.
Because alpha K,
Well. Okay. What different subscripts? Where?
On the left-hand side of the equal sign? Yeah, right there, that's why I was checking
Oh.
it.
Yeah. But then I substituted what this is.
so when
Okay.
we figured out what alpha K was earlier,
Right.
it's PK or PK transpose times PK
Don't we just get
over
0?
PK transpose A PK.
Yes, we can substitute that in here.
Don't we just get 0 though? and make
Yeah,
it
we
one?
will. Which is what the goal is. Yeah. So we take this formula for alpha K, stick it in here, and you see, oh wow, everything cancels
I
out.
didn't know the goal. I'm
Oh,
sorry.
okay. Yeah. Oh, this perpendicular to that. Yeah. Okay. All right. So yeah, each search direction is orthogonal to the previous search direction, but let's talk about the 2x2 case. How many distinct perpendicular directions can you have? You saw what happened in the plot. Start with initial guess, go a certain point, and then this again. So, given this law of nature for steepest descent, that each direction must be perpendicular to the first, I have to do that.
So you really only have 2 directions.
Right. So, this direction may be perpendicular to this one, but it's parallel to that one. You're going over old ground. So, for an n by n system, and you don't want to have that happen. You have n distinct orthogonal directions. You like to have, so in other words, we could say that steepest descent has no memory. That orthogonality only goes back one step, but the progress is going to be very slow. So if you could make sure that each new direction was somehow at least independent, like linearly independent, of all the previous directions, and if you get them orthogonal, that'd be even better. Then at least you could guarantee convergence after n steps, because you would have exhausted all your directions. Now, if n is large, that's still a lot of steps. We'd like to do better than that, but so that's why something needs to be done to steepest descent to try to improve it. And actually, well, I have this all fleshed out in the notes, but I think just for fun, well, I only have 5 minutes left for today, so I think we'll just continue this on Tuesday. But what can be done is anything that you maybe try to tweak it somehow could be what makes the difference. So, alternative is to set your search direction not just equal to the residual, like steepest descent did, but we'll add something to it. I just want to see what, to keep my notation consistent. Okay. So we will make use of the previous search direction, whatever that was, times some scaling parameter, which I'll call mu k. So that way, in case, so this idea is like to prevent us from getting stuck, if you will. So it's only a framework because I still haven't said, how do you choose this? And we have to have some criteria for that. Now, for the very first search direction, you can go ahead and use steepest descent, like P1 is equal to, or P0 is equal to R0, something like that. But then after that, we do this kind of tweaking, and we just need some decent way of choosing this. And there's also a question of, now how will alpha k be chosen? That's going to be different. So this is something we'll start taking a look at on Tuesday, that we need some sort of criteria to try to ensure this universal independence of all search directions, that each one is independent or in some way orthogonal, preferably, to all of them, not just the previous one. Okay, so Saturday, Tuesday is fine. All right, and I guess I have some code to put up on the site.